Hello everybody, this is my talk about expanding the LVFS ecosystem, and it's yet another talk about how the Linux Vendor Firmware Service has grown over the last year, and also some of the new kind of cool tricks we've taught FWD as well. So just to recap, I've worked for Red Hat for about like 15 years now, worked in open source longer than that. And I've been working on firmware for about 5 years now. So some of you might have seen these talks before for OSFC. So I'll just do a really quick recap for anyone that's not familiar with some of the stuff here. So the very first project is the LVFS. This is the like essentially the website where vendors upload firmware. We scan the firmware, and I'll explain how we're scanning it in a new way soon, and we sign it. Users then download metadata from that shared server, and it's now like, what was it, like 3,276 different devices, with a lot more kind of in progress. That metadata gets used by the client-side program, which is called FWD. And that deploys using like 32 different update protocols, which is things like DFU, Update Capsule, Wacom, Logitech Kid++, etc. And there's another, I think, 4 or 5 in development. And both projects seem to be healthy with new contributors and are growing. And unlike an FTP site, we have some visibility of how the firmware is being deployed itself. And so we get, if there's a problem with firmware deployment, we have some debugging information that we can request from the user, which makes it easy to work out things like we needed a newer kernel, so we need to add that as a requirement to the current firmware. Just like a super quick recap. Let's do the same recap on the architecture. This diagram has grown slightly. So we use dbus to talk to the daemon itself. This is a desktop neutral language. We can interact from basically any language. We integrate with the desktops, both GNOME, KDE, CLI, and even things like Red Hat Insights, which can provide some sort of site-wide visibility on things. We host everything on AWS. We scale on like 2 data centers. We auto scale. So we're planning for like an order of magnitude more firmware updates in the future. We're still designed to be decentralized. So if you're someone like the NSA or Pixar or wherever, you can basically mirror the entire LVFS and then run all your infrastructure offline and still use the firmware updates from the LVFS. So let's look at some of the new bits on this architecture diagram. I'll talk more about IPFS in a few minutes' time, but essentially what we're doing is we're allowing any non-embargoed firmware, we're sort of publishing onto the IPFS and then optionally downloading it from the client. And I'll explain why we do that in a minute. Looking at the bottom of the diagram, we now use Bluesy, which allows us to update firmware on a lot more hardware. So things like BLE mice, BLE keyboards, etc. And that's being used by Pixar, Chicone, and a couple of other vendors as well. And that's a really nice sort of set of new hardware. And talking of new hardware, we're also focusing quite a lot more on the server case now, where we might be using IPMI or Redfish to update things like the BMC firmware or the SAS or RAID firmware. And that's something, again, I'll talk about in a few more minutes as well. So the key takeaway is that it's still growing. Like LVFS grew last year like 100%. Vendors are joining. We have like 300 vendors using the LVFS now. The only notable absence really is Apple, which isn't a huge surprise. We're growing year on year. I think we'll probably hit 38 million downloads probably today or tomorrow, which would be awesome. And we're still receiving reports from end users about how the firmware has been deployed successfully or has been deployed with an error. But like I hinted just before, we don't actually know the real number of downloads. If you do like a back of an envelope calculation, you can kind of work out that it's probably an order of magnitude more than this. And if you just compare these numbers to like informally, things like Windows Update and other firmware distribution methods like that, we're basically winning. And that's something I'm really proud of. So just to recap on HSI. HSI was a specification that I kind of, I guess, previewed last year. An idea of being like a software security scan of your firmware and platform security that's done every single boot. So the OEM can use it to make sure that the ODM is providing them with the correct hardware. So things like the IOMU is turned on by default. The corporate security team, usually like Red Hat, IBM security teams, can use the same security checks to make sure that software supplied by the OEM is correct. For instance, secure boot's turned on by default, that the BIOS write enable is disabled, that the BIOS lock is enabled. And so you can actually test this stuff on hardware before it's deployed. And then actually when the hardware is in the field, you can have the user testing stuff automatically. And Kate on our team at the moment, she's been plumbing in the integration with the desktop so that we can be showing the HSI levels and the failures in part of things like GNOME Control Center. Or we can notify the user that, hey, your PCR 0 has changed before they log in and unencrypt their home directory. So I'll talk more about clever things we can do there in a few minutes again. But it's kind of giving you some sort of like recap of the bigger picture. So let's talk about some cool new things. Secure software bill of materials is a really big, it's really important right now. So firmware was explicitly left out of the recent executive order, primarily because there was no real kind of like industry tools available to the ODMs and OEMs. So it's ridiculous requiring them to do something they couldn't do. So I prototyped a project called Python USWID, which allows you to embed some very basic like entity details, like software bill of materials, entity, and licensing details into the EFI binary itself. Now, this is super important because rather than having then two files that the vendors produce, so Realtek say, hey, look, here's my EFI binary, and here's the SBOM for it, which very quickly get out of sync, or one gets lost, or they get copied and pasted and changed or whatever. It means that by embedding it into the binary itself, it means that any entities along the chain of distribution that don't understand what this SBOM thing is, it doesn't matter because it's transparently carried through. Now, because we're adding it as a separate section, the PE file, we might need to teach some AV scanners that this isn't a bad thing. And some of that's already happened with the recent SBAT work, so that should be fairly easy. Now, if we have all this high quality metadata, which has hopefully come from ODMs, OEMs, IBVs, etc., we can display graphs like the one on the left. Now, the one on the left is completely fictitious, but it kind of shows you that a typical firmware might come from mostly Phoenix, some Lenovo, some Realtek, some stuff we just don't know. We have no idea where it's come from. And in the future, we can have maybe like a stick where if a firmware doesn't have a certain percentage of SBOM for all the file volumes that are included in it, then the uploader has to click something or get some sort of waiver from a QA user or something. Now, it's really hard to get the ODMs and the OEMs to do stuff like this. They haven't got any other tooling. So a researcher at Eclipsium has been working on adding this kind of support into the EDK2 build system, which would mean that we automatically get an awful lot of SBOM metadata like by default, so to speak, before it gets taken into like the ODMs and had other stuff added. And the ODMs that don't understand what an EFI binary is are probably going to struggle with using obj-copy on the command line. And so we've designed this very simple ini style override so that if you're a distributor for this EFI binary, you can use a 2-line ini file and one line of Python code to embed that entity into the software bill of materials. So you can make it really simple and maybe even include it on the ODMs or the OEMs build pipeline for firmware. Now this could be cool and it might be useful in the ecosystem. It doesn't fix all the problems, like it doesn't solve the problem like how do you tag the MFS or other like data sections within file volume that aren't EFI binaries, but it maybe gets us some of the way there. It might be interesting. So changing the subject completely, on file upload, like I kind of hinted, we take the EFI binary, take the upload and break it into EFI binaries. And now we have the EFI binary, we can actually do some really clever scanning on this. I've been working with a company called Benali. Benali have been writing all these rules called UFI-R2, and that allows us to scan the binaries themselves for known CVEs. And here you can sort of see it's looking for the BSSA vulnerability. Benali have got another, I don't know, half a dozen different scripts which are checking for other vulnerabilities which haven't been released yet. Now this allows us to do two things. One is verify that the firmware fix, sorry, the CVE fix hasn't been regressed in a next firmware version. So if there's two parties updating the same hardware on the LVFS, that one person fixes it and then the other team undoes the fix. So we can check if the fix goes backwards like we do microcode versions. But we can also, more interestingly, work with people like CERT when they say, hey, we've got this vulnerability reported against HP. Does it affect any other vendors? And we can scan all the firmware on the LVFS with this new rule and find out which vendors we need to add to the coordinated disclosure list. And it's really interesting working with CERT and companies like Benali in this way, where we kind of collaborate, which is this thing usually with coordinated disclosure, it's just the last minute panic. And it's really nice to have this kind of structured way of notifying vendors about affected hardware. But of course, if the vendor doesn't upload firmware on the LVFS, we don't know about their firmware. But that's kind of like the cost, I guess. So changing subjects again, we've worked with 3MDeb. They've contributed all of the changes to make FWD work on FreeBSD. And there's a couple of customers that are using this on big deployments, and that's awesome. They also included the supported the CI system. So that means that we can't commit stuff which accidentally breaks FreeBSD because they're using some Linuxism. Again, on UFI, we've added support for capsule on disk. This is a different kind of, rather than using the capsule loader, some devices, by setting a EFI OS indications variable, they can say that actually the firmware will support reading the firmware out of your EFI system partition. This is super because it allows us to support some really important ARM platforms, which I can't talk about, but will be awesome. And it's kind of yet another thing that FWD will now support. Now, in a slightly less awesome side of this, we also have some systems which have broken firmware, which means that whenever you change the boot order, like boot next or the boot variables, it can actually corrupt the other boot variables. So there's something like Asus laptops that do this. Similarly with Lenovo, on corporate machines, if you have the BIOS locked, where you can't, like, you haven't got the admin password because it's a corporate laptop, you might have boot order lock set, and that basically reverts all the changes that user space does on next reboot, which means the firmware update won't run. And so instead of running shim to UFI loader, we can now run shim to grub to UFI loader, which is like an extra step, which means we can get around these systems where we can't modify the boot variables or boot order lock is set. So something else which was asked for by the Chrome OS team was a global progress bar. Now at the moment, in the pathological case, it could be where, say for instance, you've got a dock with, say, like, I don't know, 12 different USB devices in this dock, which are all kind of one thing. And each of those USB devices might have a raise phase, a write phase, a verify phase. And there could be multiple devices updated in one sort of firmware update. So the progress bar will go back and forwards, maybe, well, indeterminate number of times, but maybe dozens of times. And that's just not great for showing any UI. So we've scattered lots of code in all the plugins now, which basically tell the daemon what proportion of time is spent doing each phase. Now, rather than putting in, this is going to take 6 seconds or 2 seconds or 100 milliseconds, that changes on how fast your processor is running or whether you're using USB 3 or USB 1. And so we put in like a proportional thing. So here we're saying that it's busy 1% of the time, erasing 20% of the time, writing 45, verifying 35. And these numbers aren't that important, and the daemon will tell you if you get them wrong, and it will tell you the right numbers for them. But it basically means that by telling the daemon what step of the process you're at, it can work out the proportion within the current phase. And so if you have to run like 2 transactions, it means that you get the kind of the correct global progress. So given an example, this is installing on a Wacom drawing tablet. And inside the Wacom tablet, there's actually a USB hub, there's a USB radio and a USB system firmware. And this is installing, first of all, onto the system firmware inside the Wacom tablet. And here you can see they're going through the writing phase, and then it's going into a read verify phase very quickly. Now, unusually with the Wacom tablets, you need to reboot the device so that you can be running the new system firmware before you can update the radio firmware. And so here you can see it's restarting the device, and now it's started writing the radio device, which happens quicker, but the amount is shorter. And then we reboot again, reboot, find the new firmware version, and that happened all with just 1 transition from 0 to 100. Because when you're building a GUI, you see this nice, beautiful bar that goes up kind of like linearly, rather than jumping around or resetting back to 0. So of course it makes the UI of the command line nicer as well, but it means we can improve the things like GNOME software and any of the KDE tools as well. So let's look at a bigger problem. Now, I've been working with Lenovo server team for, I don't know, about less than a year, I guess, because this is what customers were doing before. Customers wanted to not use the enterprise kind of like fleet management stuff that the OEMs were producing. They wanted to basically run the firmware updates on their terms. So they'd update like 80% of the fleet on day 1, 10% on day 2, and the rest of the 10% on day 3. And they'd provision it using some usually company-specific provisioning agent, which meant they were using the low-level tools rather than like Xclarity or some high-level thing. And so things like UXPI is one that customers would use quite a lot. UXPI is, well, it was built in 2014, hasn't been updated since. So it's using horrible versions of OpenSSL. Even worse, last year, the certificate that it uses for transport expired and was never renewed or changed or modified in any way. And so you have to do horrendous things to OpenSSL to actually get it to run at all. And it doesn't actually work on RHEL 8 anymore, it only works on RHEL 7. And so the consequence is that users just weren't updating their Lenovo servers using RHEL. And we can do a lot better. And the way the industry has kind of moved, it's moved to this thing called Redfish. Redfish is like this open specification, DTMF spec, where we can just talk to the BMC and say, hey, update this with that. And that's the kind of the goal. Now I put in the slide Redfish-ish. So 99% of the specification is common between vendors, except the 1% that is massively different. And Lenovo, to their credit, anytime that we found areas where XCC had a non-compliant implementation of Redfish, they've done really well and fixed the XCC implementation so that it actually matches the spec. But of course, FWD needs to support updating from the old version as well. And so we need to support all these quirks. So these HPE quirks, these Lenovo quirks, these iDRAC quirks. Now, the way this works at the moment is you can either provision on your host OS, like a username, passwords, a URI, etc., for the box itself. But that sucks because you want it to just work. You want to install RHEL 9 on your very expensive server and for it magically just to work because you can update firmware. And so the way we do that right now is there's a SMBIOS table called type42, which tells the host OS what internal network adapter, usually USB or something, to connect to get to the BMC. Now, it's slightly complicated in RHEL because you need to tell network managers to bring that interface up because it's not by default. But once you're there, you can actually talk to the BMC. But you don't have any login credentials because there's no kind of like, it's not like it's hard-coded username password. And so we actually use IPMI to provision a Redfish user account. And then once the IPMI step's done, we can then use Redfish to do all of the other firmware actions and we don't have to care about IPMI anymore. There are other ways of doing this. You can have an ephemeral username password combination sent to the host OS by the BMC, but no vendor seems to do that, and so it doesn't work in reality. Now, it might be unusual to think about updating things on the BMC through FWD, kind of where FWD acts as like a proxy, and it seems like a weird way of doing it. Why don't you just connect to the BMC using Redfish? But it turns out a lot of customers, even though the BMC has an external network port that you can just connect to your management plane of your data center, most of the customers don't actually use that, either because they don't trust the HTTP implementation and the Redfish implementation enough to be on a separate data plane, or because they want to use the same tools they're provisioning and updating the host OS. They want to use those same tools for updating the firmware. The other reason is the host OS kind of needs to get involved for the devices the BMC doesn't know anything about. Things like ATA devices, NVMe, if they're not shared, DFU, any input devices, etc. And so we have to kind of coordinate between the two. Now, this does mean that you get to use the dbus interface of FWD to update stuff using Redfish through the BMC, which is kind of like an extra step. But it means then you can, anything that can talk FWD can then report firmware details. So for instance, we've integrated it with the Red Hat Insights product, so that if you deploy RHEL onto your whole lot of servers, you can see straight away which ones have insecure firmware, which ones have BIOS lock enabled, not enabled, and you can do it that way as well. If you're provisioning, you can also just provision username and password credentials if they're hard-coded as well. So it kind of works, and I've been testing this with Lenovo, and they're super happy. And I kind of hope the same thing will happen with Dell and HPE as well. Now, maybe the next idea is maybe either crazy or genius, and I don't know which yet. So you can actually run FWD on the BMC itself. And so I finished this just last night, like 4 in the morning or something. And you can compile OpenBMC with FWD support, flash it onto the BMC itself. And then when you SSH into the BMC or use web console or something, you can actually enumerate all the devices the BMC can see. Now, typically, this is probably just your MTD devices. But that might be sane. That might be good enough, because that means now you can SSH into a BMC and update all your the BMC firmware itself using the same tools that you would do on the host OS. I don't know if this is crazy or this is genius. I've not decided yet, but it might be useful to some people. And it kind of shows that FWD is small enough and it is kind of self-contained enough without so many dependencies that it does kind of work in this super embedded case. Now, on the ecosystem side of things, we have this idea of having a signed report. So the idea is that the OEM or the ODM or even the distro QA team can actually say, yep, I've tested this on this exact hardware and it definitely worked. And here it's signed to make sure that that's correct. And so Lenovo have started doing this for their ThinkPad firmware updates. So you can actually see it's been tested and what it's been tested on. And I can kind of see like distro QA teams also doing this as well. So that, for instance, if you had a Red Hat customer who said, I only want to deploy firmware updates that have been tested by Red Hat on my fleet, you could have that, because all of this data is in the public metadata. You know who's tested what, when, and so you can use this for your sort of fleet management provisioning. That's kind of cool. Another thing we're starting to do now, but we're kind of hampered by the kernel at the moment, where the kernel, you can only do this stuff with secure boot turned off, or there's some patches which may allow this in the future, where you can have you can use the Intel SPI controller. But at the moment, we have to do this from user space and do ungodly things to the PCI controller to unhide PCI devices. But essentially what you can do is you can actually drag the system firmware off the SPI chip at user space and export that as a device in FWD. which might seem maybe not so necessary or not so interesting, but it lets you do some quite cool stuff. So rather than before, where I kind of said that you could say to the user, hey, your PCR 0 has changed because you've gone through airport customs and someone took your laptop to a room for 10 minutes. But now you can actually say, hey, your PCR 0 has changed. And we know that there are now 3 extra EFI binaries inside one of the file volumes, which get run at startup, and you really shouldn't trust your laptop anymore. And so we've developed the parsers that can parse all of your system BIOS every single boot, and deserialize and process and look for stuff on client side rather than server side. This is also weirdly worked out nicely for fuzzing as well, because if we take out some of the alignment requirements, we can produce almost completely a valid IFD image that's a few kilobytes in size, which contains all of the right partitions in the right places and all that kind of thing. And then you can fuzz it, and fuzzing works really well with very small files with lots of very dense parsing, and it works really, really well. And maybe you could use this for fuzzing the actual hardware. If the hardware isn't so critical with the alignment stuff, maybe that makes sense as well. So there's some really interesting things we could do with that in the future as well. For me, this is really useful for making test files. I can make an IFD in I don't know, 40 lines of XML of hello world content in all the EFI files, and that's really useful. So talking very briefly about IPFS, I mentioned it before, but essentially if there was a country that had a not so great firewall, all the firmware coming off the LVFS looks like an encrypted blob, which causes it to freak out. And rather than getting 200 ksec, you're getting 5 ksec. And that's a problem if you have XCC firmware, which might be 100 megabytes in size. That takes an awfully long time to download. And so we now upload anything that's not country embargoed. So Dell firmware can't be downloaded from Syria or Afghanistan, etc. And so we don't upload that firmware. But all the rest of the firmware that can be downloaded from any country, we upload to this IPFS, and then on the user space, you just do the normal FWD-MGR updates -- IPFS, and then it grabs it from your local IPFS node. So if someone in, let's say, China downloaded the firmware and had it locally, you get that firmware from another user in the same country rather than having to go to the US. Of course, that means we don't get the download stats anymore, but I'd much rather users had updated firmware than the counter on the wall went up slightly faster. So that's basically all I had to talk about today. I think there's 3 things we should push for. One is that silicon vendors should continue to support HSI, right down to Intel, AMD, VIA, Realtek, etc. I really want to push harder OEMs, not just OEMs who make laptops or kind of desktop systems or servers, but even the vendors like kind of the Asuses of the world that produce motherboards you go and buy in Best Buy or something. And you want to be able to update the firmware on those gaming laptops, gaming hardware, as well as just the laptop that's come from some big OEM. And also, I think the only real way of pushing this even further is making the LVFS part of these corporate purchasing requirements. We've already had some governments and some companies doing this right now, but if you make LVFS part of these requirements, it means that you either stop vendors from selling stuff they've sold to people before, or you allow them to sell to a new market segment they never sold to before. And either of those things make them do what you want them to do. And that's awesome. So thank you very much for listening. Hopefully next year I'll sort of see you all in person. And if you've got any questions, I'm happy to answer them in a few minutes. Thank you.